Hey guys, welcome back to a new video. In this session we'll be solving 3 real-life problems step by step on uniform circular motion. We'll be using and explaining concepts like radians as the SI unit of angles, angular velocity and real velocity, and how these latter two are connected to each other. In particular, we'll be calculating the velocity of the endpoints of the wings of a wind turbine at sea. And we'll see that this velocity is actually similar to the velocity of a small passenger plane. We'll also be calculating your velocity with respect to the Earth's center. And this velocity, it turns out, will be twice the velocity of a small passenger plane. And to end off, we'll address one of the most common misconceptions about launching rockets into space. We'll be calculating the drift of a Starlink satellite with respect to the Earth's surface if we were to simply shoot it straight up into the air. The timestamps of each of these exercises can be found in the comment section below. And with that intro out of the way, let's get into the first exercise. In the first exercise, we're going to be looking at a wind turbine at sea. I imagine by now we're all familiar with the image of a vast number of spinning wind turbines at sea. And if you watch footage of these spinning wind turbines and you close in on one in specific, then you will see that on average they will make one revolution each 4 seconds. We also know that these wind turbines at sea can be made much larger than the ones we have on land, with the largest wind turbines at sea having wings of over 80 meters. So let's not take an extreme case and let's simply go for 70 meters. And given that the wind is constant and that the length of these wings does not change, we know that the endpoints of these wings will make a uniform circular motion. And the problem that we're going to solve now is to calculate the velocity of these endpoints when indeed our wind turbine is spinning at 4 revolutions per second. And we'll be able to solve this in 2 simple steps. The first step is to calculate the angular velocity of our wind turbine. Before we calculate the angular velocity, let's first make sure that we understand what it is. At any point in time, we can draw an angle of this wing with the horizontal axis, and we call this angle theta. And because our wings are spinning, this angle theta will change in time. And we know that a distance that changes in time gives a velocity in meters per second. An angle that changes in time gives an angular velocity. And we could denote this as being degrees per second. For example, the angle changes with 1 degree per second. However, for angular velocity, we're actually using the unit radians for angles. So the angular velocity, v theta for example, will be in radians per second. Alright, so the concept of angular velocity is clear. It's basically how fast the angle is changing per unit of time. However, what exactly is this unit radians? Well, to understand this, let's draw a circle with radius r. We know that radian is a unit of angle, so we're looking at an angle here. Let's now take our radius r and plot the same distance r as an arc length along this circle. If we then connect the middle of our circle with the endpoint of this arc length r, then this angle will exactly be 1 radian. And this is how radian is an alternative unit for angles. This definition also allows us to make a conversion formula between degrees and radians. We know that all the way around is 360 degrees. And now we wonder how many times this arc length r fits inside of this entire circumference of the circle. Well, we know that the entire circumference of a circle is simply 2 pi times r. And therefore, together with the definition of 1 radian, we know that 260 degrees will therefore be 2 pi radians. And from this equation, we know that 1 radian is approximately equal to 57 degrees, which is of course 360 degrees divided by 2 pi. So now that we know what a radian is, we can very easily calculate our angular velocity. Because we know that the wind turbine spins 1 time around in 4 seconds, we know that 1 time around is exactly 2 pi radians, which we just saw, and it does so in a time of 4 seconds. And therefore, we know that the angular velocity is equal to pi over 2 radians per second. which is approximately 90 degrees per second. And again, this velocity that we just calculated, the angular velocity, is simply the rate of change of this angle that the wings make with the horizontal axis. However, this does not say anything about the actual velocity of these endpoints, because for this we would want a true velocity in units of meter per second. So how do we get from this angular velocity to our true velocity? And for this, the formula is very straightforward. We know that our normal velocity is equal to r, our radius, multiplied by our angular velocity. And in our case, our radius would be 70 meters. And our angular velocity would be pi divided by 2 radians per second. And this turns out to be approximately 110 meters per second, which is the velocity of the endpoints of our wind turbine. Let's now, for good measure, convert this to kilometers per hour. So we have 110 meters per second. 1 meter is 1,000th of a kilometer, because 1 kilometer is 1,000 meters, and 1 second is 1 over 3,600 hours. Doing this calculation, we find that the result in kilometers is 369 kilometers per hour. And this is exactly the speed of a small passenger plane at liftoff. This means that the wings of these turbines need to be able to experience enormous forces, and this has to be taken into account producing them. Let's now go to the second exercise. In the second exercise, we are going to be calculating your velocity with respect to the Earth's center. Now, of course, you will have this velocity because you're standing on a rotating Earth. We know that the Earth rotates one revolution in 24 hours. In the first scenario, we're going to be considering the most simple case, where you're standing at the equator. And then in the second scenario, we're going to be looking at when you would be standing at 28 degrees. Intuitively, you can already see that your velocity will be smaller. Because you're standing closer to the North Pole, your distance from the rotation axis of the Earth will be smaller, and therefore your velocity due to the same rotation will also be smaller. How much smaller this is, we will calculate exactly. There is one more piece of information that we need in order to solve this exercise, which is of course the radius of the Earth, which comes out to be an average of 6,371 kilometers. Again, we will calculate the effective velocity by first looking at the angular velocity. As we know, the angular velocity is expressed as radians per time unit. In this case, one full revolution is 2 pi radians. And we know that the revolution takes approximately 24 hours. This can be calculated as being 2 pi radians divided by 24 multiplied by 60 multiplied by 60 seconds, because 1 hour is 60 minutes and 1 minute is 60 seconds. And this can be calculated to be 7.27 times 10 to the power of minus 5 radians per second. And this is the angular velocity. From the angular velocity, we can of course calculate the real velocity in meters per second. This will simply be r, the distance from the rotation axis that we're looking at, multiplied by the angular velocity. In the first scenario, we know that r, the distance from the rotation axis, is equal to the radius of the Earth. And we know that the angular velocity is the one that we just calculated. So we can multiply these two numbers, 6,371 times 10 to the power of 3 meters, because 1 kilometer is 1,000 meters, multiplied by 7.27 times 10 to the power of minus 5 radian per second. Using a calculator, we find this to be 463.3 meters per second. Or again, converting this to kilometers per hour, we have 463.3 multiplied by 1 over 1,000 kilometers, because 1 meter is 1,000th of a kilometer, and 1 over 3,600 hours. because 1 second is 1/3600th of an hour. Using a calculator again, we find this to be 1667 kilometers per hour. And this is actually the speed by which you are traveling through space with respect to the Earth's center, simply due to the rotation of the Earth. However, this was the case if you're standing at the equator. And I know for a fact that the chance will be very slim that you're watching this video from somewhere along the equator. Therefore, let's go to scenario 2, where we will calculate this exact velocity, but now from any point on Earth. To do this, let's draw a cross-section of the Earth, and let's draw now the rotation axis as being the y-axis, and it points straight up. So we have the x-axis here, and we have the y-axis. And as I said, we are considering the case where the rotation axis of the Earth is now purely vertical. So we tilted our original sketch a bit. If the rotation axis is vertical, then we know that the equator will be horizontal. And we know that the distance from the middle of this cross-section to the surface is of course r. And we've already calculated in the previous scenario, we calculated the velocity you would have if you were standing on the equator. However, now we're going to be calculating what your velocity will be if you would stand at another place on Earth. For example, at 28 degrees. In this case, the distance from the surface to the rotation axis will denote as r prime, and r prime is clearly smaller than r, the radius of the Earth. So let's consider what your velocity will be if you would be standing right here. We can actually use a very simple geometry to figure out this distance r prime. Let's connect these two lines and call this angle theta. We know that theta in our case is 28 degrees. This was simply a given. This means that this distance right here, which is also the distance r prime, is of course equal to the cosine of this angle theta. Therefore, we can write that r prime, which is the distance from the surface at 28 degrees to the rotation axis, is equal to r, which is the same distance but at the equator, so the radius of the Earth, multiplied with the cosine of this angle, theta. And in our case, theta will be 28 degrees. However, you can easily look up your specific angle so you can calculate your own velocity wherever in the world you are. Let's calculate this. So r is equal to 6,731 kilometers. And we multiply this with the cosine of 28 degrees. And this turns out to be 5,625 kilometers. So at this point on the Earth's surface, you're actually 1,100 kilometers closer to the rotation axis than if you would be standing on the equator. And of course, at this point, we can calculate your velocity at this specific point, because the velocity is equal to the distance from the rotation axis, in this case r prime, multiplied with the angular velocity. So this will be equal to 5,625 kilometers multiplied with 7.27 times 10 to the power of minus 5 radians per second. And if we calculate this, we end up with 409 meters per second. And again, converting this to kilometers per hour, we have 1,472 kilometers per hour. And this velocity is notably less than the velocity we had before. Before we had 1,667 kilometers per hour. And now we have almost 200 kilometers per hour less. So when you're residing at the equator, or when you're residing at 28 degrees, your velocity compared to the center of the Earth will be notably less. In this example, 200 kilometers an hour less. Let's now go to the third and last exercise, where we are going to consider the drift of a Starlink satellite. In this problem, we are again considering our rotating planet. And let's consider that we have a launch base at the equator, and we launch a rocket with a Starlink satellite straight up into the air. We know that Starlink satellites orbit at around 550 kilometers above the Earth's surface. And since we're launching this satellite straight up into the air, we're not giving it a velocity that is pointing in the plane of the Earth's surface. And therefore, with respect to the rotation axis of the Earth, the Starlink satellite will actually have the same velocity as the Earth's surface would have. And this can be quite confusing, so let's see exactly how this works by again drawing a cross-section of the Earth and our two axes. And this cross-section is actually looked at from the rotation axis itself. And therefore that we know that the Earth is actually rotating in that direction. So we have a top view of the Earth. And we also know that the circle drawn here is therefore the equator. And thus the equator is traveling at a velocity of 1,667 kilometers per hour, what we calculated in the previous exercise. Let's now consider that we're launching the Starlink satellite straight up in the air. This means that the path it will follow will be an extension of the line connecting the center of the Earth with this point on its surface at the equator. So it will be this direction, and our satellite will actually be somewhere right here at a distance of 550 kilometers from the Earth's surface. So what do we now know about the orbiting velocity of this satellite? We know that these satellites will also be orbiting in the direction that it initially had when it was still on Earth. And we know moreover that because we are launching the satellite in a straight line up from the Earth's surface, that the orbiting velocity did not change from when it was on the Earth's surface. Therefore, we know that this velocity and the velocity of the Earth's surface is exactly the same. This means that the Starlink satellite and yourself standing at the Earth's surface will actually have the same velocity. However, you might already see what is going on here. Even though you and the Starlink satellite have the same velocity in the orbiting direction, you actually have to travel a lesser distance than the Starlink satellite would have to travel, because the Starlink satellite is 550 kilometers further away from the rotation axis. And therefore, when time goes on, the Starlink satellite, even though it has the same velocity, will start to drag behind your location on the Earth's surface, so it will not remain directly above you. And what we're going to be calculating now is at what velocity the Starlink satellite will be drifting away from being right above you. And to do this, we are going to be calculating the velocity that the Starlink satellite should have in order to be staying directly above you. And we already know that this velocity will have to be larger, because it will have to cover a much larger distance in the same time as you would. So what does it actually mean for the Starlink satellite to remain directly above you at all times? Well, this means that both you and the Starlink satellite should have to make the same angle theta with the x-axis at all time. Because if these angles are the same for you as for the Starlink satellite, the satellite will remain directly above you. And because both you and the satellite are orbiting around the rotation axis, this angle theta will have to be the same at each point in time. And therefore, the angular velocity will have to be the same. We have already calculated that the angular velocity for being stationary on the Earth's surface is 7.27 times 10 to the power of minus 5 radians per second. This is the angular velocity for being on the equator on Earth, and therefore will have to be the angular velocity of the satellite in order for it to be constantly directly above you. So from this, we can calculate the actual velocity that the satellite should have for it to be directly above you. We know that this will be the distance from the rotation axis r multiplied with the angular velocity. Now, what is the distance to the rotation axis? It is the radius of the Earth plus this 550 kilometers above the Earth's surface that the Starlink satellite is orbiting. So this will be 6,371 kilometers plus 550 kilometers multiplied by 7.27 times 10 to the power of minus 5 radians per second. And this will of course be equal to 6,921 times 10 to the power of 3 meters multiplied by 7.27 times 10 to the power of minus 5 radians per second. Calculating this, we find it to be equal to 503 meters per second, and converting it again, multiplying by 3.6, is 1,811 kilometers per hour. And again, to be sure, this is the velocity that the satellite should have if it wants to remain stationary directly above you, right here. However, we know that this is not the case because we do not give the satellite any velocity in the orbiting direction. And therefore, its orbiting velocity will simply be the orbiting velocity of the Earth's surface at the equator. Therefore, we can calculate the difference in velocity, being 1,811 kilometers per hour, minus 1,667 kilometers an hour. And this comes out to be 144 kilometers per hour. And this will then be the velocity by which the Starlink satellite is drifting away from you. Simply because it has the same velocity as you do, but it has to travel a much further distance. So on our initial sketch, we calculated that the trailing of this Starlink satellite will be at a velocity of 144 kilometers per hour. However, there is of course a massive flaw in this exercise, namely that we simply do not send satellites into space like this. This is not how we launch rockets. If we would launch rockets like this, then they would simply fall straight down again. However, how we do launch rockets is not by launching them straight up in the air and not giving them any velocity parallel to the Earth's surface, but giving them a lot of velocity in the Earth's surface such that they are flying at enormous speeds parallel to the Earth's surface. And how this exactly works, we will see in another video. And this brings us to the end of this video, and I hope that you really learned something and are now more familiar with uniform circular motion. If you learned something, give this video a thumbs up. If you have any questions, leave a comment in the comment section below. And if you really enjoyed watching it, consider subscribing. And with that, I see you guys in the next video. Take care. Bye.